All right, today's notes, 1.7 part 2, we're continuing with our conversation around transformations of functions. Our objective today is to apply composition of transformations to the graphs of functions and use transformations to write equations from graphs. So more than just understanding what our values of a and h and k are doing to our parent functions, we want to be able to apply multiple transformations to a parent function and do that correctly and in the correct order. So first and foremost, we have this warm up here today. We'll work on this one together. So I see a parent function f of x, and if I had to think about what family of functions does this shape belong to, this v shape, I would know that the parent function for this is f of x equals the absolute value of x, because this is an absolute value function. Absolute value of 1 is positive 1, absolute value of negative 1 is also positive 1. All right. Now, what I see is that we have this other function, g of x. Well, g of x looks like it's been stretched vertically, meaning when I go right 1, up 1, this graph goes right 1, down 1, 2. So that tells me a couple things. Number one, it's been flipped over the x-axis. And two, it's been stretched. So the number that I'm going to multiply, if I multiplied the parent function by something, this value for a, the absolute value of a, would have to be greater than 1. So I'm seeing that g of x should be negative some number times the absolute value of x. And to figure out what that number is, we're going to see how the vertical distances vary. So here it was, if I went right 1, it was up 1. Here, if I'm right 1, it's down 2. So that seems like the vertical distance, even though it's flipped over the x-axis, is being doubled. So from here to here is just 1, but from here to here is 2. Let's see if that holds up from here to here. So from here to here is 2. From here to here, 1, 2, 3, 4 is 4. So yeah, the vertical distances are being doubled. So I know that that means my graph for g of x should be equal to negative 2 times the absolute value of x. 2 stretches it, makes it narrower, and then the negative is what flips this whole thing over the x-axis. Okay? Let's move down a little bit here, and let's look on the left. So first of all, this is like super duper important right here. All right, right here it says g of x, whoops, says g of x equals a. We know what that a does. It's that dilation. It stretches or compresses, times f of x minus h. We know h is that value that moves it left or right, and then k plus k means we know there's some value that's going to move this graph up and down. All right, so where f of x is the parent function, what do all these things do? Well, the value of the absolute value of a stretches or compresses, it dilates the parent function. When the value of a is negative, the graph is reflected across the x-axis. This is all stuff we learned in the previous lesson. The value of h shifts or translates the parent graph left to right. Remember, if h is positive, it goes right. If h is negative, it goes left, although be careful there because it appears to be the opposite. And then lastly, the value of k shifts the parent graph up or down. Okay? Then, on the left here, this is new today. So if we had to put an order to our transformations, it would be HSRV is what I'd like you to remember. HSRV helps us remember to do the transformations in these order. So horizontal translation first, so that's the left or right. Then our stretch or shrink, that's our dilation, our reflection over the x-axis, and then our vertical up or down. Okay. If we come over here and look at these graphs, we can kind of take a look at all these different transformations. So a dilation, remember, when the absolute value of a is greater than 1, it's stretched vertically. When it's a fraction between 0 and 1, it's compressed vertically. So stretch means it gets narrower, compressed means it gets wider. It's all in proportion to the y-axis. A stretch would be a multiplier of a number greater than 1. A compression would be a multiplier between 0 and 1. Remember, a reflection is when that value for a is negative. All right, so we know that this function is going to get flipped over the x-axis when a is a negative value. Then for our horizontal and vertical translations, when h is greater than 0, the graph moves right. H is less than 0, the graph moves left. Vertically, when k is greater than 0, it's moved up. When k is less than 0, it moves down. Okay? So those are the main things to remember about our transformations. So let's look at example 5 together. All right. Example 5, multiple transformations of functions. Describe in your own words how the graph of g of x equals negative 2/3 times the absolute value of x plus 3 plus 1 is related to the graph of the parent function, which is f of x equals, and remember the parent function is just the simplest form of that function family. Well, since it's absolute value, we know the parent function is just the absolute value of x, okay? So in our own words, what's going on? Well, here's what I see. I see a graph, a parent function graph that's moving left 3, okay? It's being compressed by a factor of 2/3. It's being flipped over the x-axis because the 2/3 value is negative. And lastly, it's moving up 1 unit. So in the HSRV order, horizontal left 3, stretch or shrink, this would be a shrink of 2/3, reflection, yes, over the x-axis, and then vertical, our k value is plus 1, so moving up 1. Can we identify A, H, and K? Absolutely. A in this case is negative 2/3. H is actually not positive 3, but negative 3. And then K is 1. Now, a lot of you are going to have questions. Why is H negative 3 again? Remember that the general form is right here. General form, it's x minus h. So x minus negative 3 is how this shows up as an x plus 3. This part is really absolute value of x minus negative 3, right? So we need to account for that. Do you know how A, H, and K impact the parent function? We just talked about that. A does two things. One, it compresses it. And two, it's a reflection over the x-axis. H moves left 3 units. K moves up 1 unit. So that's how we know how it impacts the graph, okay? Let's take a look at the vertex, see if this makes sense at all. So left 3, that's going to be 1, 2, 3. The graph is going to be wider. This one appears to be wider. It's flipped over the x-axis, and then it shifted up 1. Absolutely, that's where we would land. Okay. All right, example 6, apply transformations of functions. Suppose the path of a dolphin during a jump is modeled by g of x equals negative 0.0125 times the quantity of x minus 12 squared plus 18, where x is the horizontal distance traveled by the dolphin and g of x is its height above the water. Describe how the path of the dolphin is related to its parent function, f of x equals x squared. All right. So let's do it in order of operations here, in order of transformations. Horizontal, 18 is greater than 0. 18 is this, oh gosh, that's not the right one at all. I meant to put 12 here. Sorry about that. 12 is the horizontal shift, right? 12 is greater than 0, therefore g of x is shifted 12 units to the right of f of x. 12 units to the right because 12 is greater than 0. Stretch or shrink, so 0.0125 is a value between 0 and 1. Therefore, g of x is dilated by a factor of 0.0125. And that would be a shrink because it's not greater than 1. Reflection. All right. The 0.0125 is negative if we look at it up here, okay? Therefore, g of x is reflected across the x-axis, okay? So here's the parent function, right? And then, boom, this one opens down compared to this one that opens up. So there's that reflection, that flip over the x-axis. Last but not least, this should be an 18. Sorry about that. We have a plus 18 out here. 18 is, let's see, I meant to put 18 is greater than 0. Therefore, g of x is shifted up 18 units, up 18 units. So fix that, okay? Sorry, a couple typos there that you need to get through, but hopefully that all makes sense. So we took this parent function, right? We did a couple things. We shifted it right 12 units, boom, all the way over here. You can kind of see that. We stretched it out, right? It became much more compressed. Flipped it, meaning it opens down, not up, right? And then lastly, we shifted that vertex up 18 units, okay? Example 7 here. Write an equation for the function graph to the right. What function family does it belong to? So what is the parent function? Well, this looks like a V shape to me. V shapes remind me of absolute value, right? My parent function for absolute value looks like this. F of x equals the absolute value of x. Okay. And so the question is, how does this compare to that parent function, which looks like this? Right? Okay, well, let's start with h. Okay, where did we shift? So this is the vertex here, so we need to come to here. How many units left is that? 1, 2, 3. So h equals -3. That's important. So this was left 3 units. Okay? Then HS, stretch or shrink, it looks like we are shrinking, all right, compressing. It's a compression, so I'm looking for a fraction number for A, all right? And the way I can tell that is here I was going right 1, up 1. Here I'm going right 1, up a touch, right? Well, this looks like 1, 2, 3, up 1. So that would be a rise of 1/3, and a run of 1. So A would be 1/3 in this case. 1/3, 2/3, 3/3 to get to here. Is there a reflection? None. There is no, it's opening up just like the parent function is. And then a vertical shift, it looks like we need to go down 1, 2, 3, 4. So my K value is -4. Okay. So now we can take all this information, 1, 2, 3, and 4, and write the equation for g of x, we'll call it. Okay, we'll call this one g of x. So g of x is going to have a multiplier in front of it. It's going to be 1/3. Then in the absolute value bars, it's going to be our horizontal shift, and it's going to be x minus -3. We'll clean that up in a second. Plus k plus -4 outside of the absolute value bars. So let's clean that up. G of x equals 1/3 times the absolute value of x. This becomes, instead of minus -3, plus 3. And instead of plus -4, this can be -4. So that is our equation for g of x. Oh, we answered all these questions on the previous page, didn't we? What transformations have impacted? There are 3. That was an H, an S, and a V. So that was a horizontal translation. It was a shrink, which was a compression, and there was a vertical. The only one there wasn't was there was no reflection. We identified A, H, and K on the previous page, so we don't have to redo that. And then we substituted all these in. Check, already did that. Let me come back here just so we have all the work here. These were the 3. Remember, this one did not count. There was no reflection, but we had H, S, and V, horizontal, shrink, vertical. We took those A, H, and K values, we plugged them in here. We simplified, we cleaned it up. So we're all good. All right. Last but not least, looks like we have another absolute value function. So we're going to start there. Absolute value parent function looks like this. Absolute value of x, right, which we know is just up 1 over 1, up 1 over 1 in both directions. So looks like I don't have a reflection again. I do have a horizontal shift. All right, so I'm shifting 1, 2, 3 to the right. So h equals 3. HS, stretch or shrink. It looks like I'm stretching out. Looks like it's getting narrower. So instead of 1, 1, it looks like I'm going 1, 1, 1, 2, 3, 4, 5. So the A value in front is going to be 5. And then V looks like I'm going up 1, 2. So my K value is 2. Okay. Again, my general form should look like this. Y equals, let's try that again. Y equals A times X minus H plus K, where X minus H is an absolute value. A is our stretch or shrink. If A were negative, it would reflect, and then K is up and down. Okay, so now let's plug these into here, right? So we're going to get Y equals, A is 5 times X minus H, which is 3, plus K. Boom. And that's totally cleaned up and looks good to me. Okay? All right, so that was 1-7 part 2. Once again, you can use this time now. Feel free to go back to the video if you need any clarification, but feel free to go ahead and work on your homework at this time.